Okay, today I want to talk about determining minimum sample size when you'd like to have some exact or less than some limit for the margin of error. You've seen this before when you look at political polls. They'll say that 52% favor a particular candidate, and then they'll say plus or minus a margin of error. They might say there's a 4% margin of error. Well, what they can do, and what they do is they start with some margin of error and then compute the sample size such that they're guaranteed to have, let's say, a 3% margin of error or a 4% margin of error at a specific level of confidence. Now, we already know margin of error on the right-hand side, let's say if this were p hat, that the right-hand side is the confidence coefficient times the standard error. So if this is the margin of error, we know a level of confidence, and we have some estimate of P and Q, and we know what margin of error we want, we can just set margin of error equal to this and solve for the margin of error. Same thing for the mean, except we'll have x bar plus or minus z sigma divided by the square root of n. That's the margin of error. If we have some desired margin of error, we'll set it equal to this. We have a level of confidence, say 95%, that's going to be 1.96, and we know or have some estimate of the population standard deviation. We'll just put that in and solve. So again, margin of error is equal to the confidence coefficient times the standard error. It's this part of the equation. Margin of error, I usually call it MOE now, because of the Three Stooges, of course. Margin of error is equal to z sigma divided by the square root, z times sigma divided by the square root of n when we're estimating the population mean. If we want to do that for and let me go ahead and say while I'm moving back and forth here, we will only do this for, we will only do estimates we will only calculate sample size when we're trying to estimate a single mean or a single proportion. We could do it for two means or two proportions or other things. It's just a matter of having more math to do. We just want to get the process of it and kind of understand how it's done. So if the problem says we want to estimate sample size and we have population proportion, looks like I'm going to have to do this every time now, and we have population proportion, then when we estimate population proportion, it's going to be the statistic p hat plus or minus the margin of error, where margin of error is z equals the square root of p hat q hat over n. So we're just taking that right-hand side and setting that equal to a margin of error. You could, as I've done here, then just solve for n, then go find your numbers from the problem, plug into that and get n. Or you can just plug the numbers into this formula and then solve after you've done that. That's actually usually what I do. So again, just an overview. The problem is going to say we want to estimate sample size. How large of a sample should we take? We want to be within this amount, or we want to have this margin of error and a level of confidence. I'll go ahead and say a couple of other things here, that when we're talking about proportions, that we might have some pilot study that tells us that we expect the population proportion to be somewhere around 0.35% or 0.35 or 35%. When we were talking about support for a candidate in the primaries or support for some political position or whatever, we think it's going to be about 0.35. Then we'll use that for P, and then Q would be 0.65 or 1 minus that. But frequently, we don't have any kind of pilot study or prior information. If that's the case, if you have no prior information, let P hat equal 0.5 and Q hat equal 0.5. The reason you do that is we have the product of P and Q. The largest product you can get is with 0.5 and 0.5 because they have to add to 1. So if you had P hat and Q hat, just give you some numbers here that they could be. That'll be enough to get you the idea. Remember, we're looking at the product of those. 0.09, 0.16, 0.21, 0.24, 0.25, 0.24, 0.21. That 0.25 is the largest. Sorry, the marker's not working as well as it usually does. Well, anyway, that's the largest you can get, so it's the most conservative estimate of sample size that you can have. One other thing I want to say before I just work a couple of problems is that you always round up. So if I ended up with 211.04, that's the minimum. Well, you can't take 211.04 in your sample size, so always round that up to the next higher number. Okay, so in this first problem, we're estimating the population mean. It says how large of a sample. That's how we know it's a sample size problem. We want our estimate to be within 25. That's the margin of error. We want 95% confidence. And we think the population standard deviation is about 400. So let's just write that down. We want to know what the sample size is. We want to be within 25. We want 95% confidence. That goes with a z of 1.96. And we think that the standard deviation is 400. You don't have to do this, but technically, since it's an estimate, the hat over there would be an estimate, but we'll just leave it as sigma, just put that in there. But anyway, when we did get around to calculating confidence interval for the mean, we already know that's going to be x bar plus or minus z times sigma divided by the square root of n. So that's the margin of error. So margin of error is equal to z sigma divided by the square root of n. And so we have 25 is equal to 1.96, 400 divided by the square root of n. I usually would just now go straight to the n equals, but I'll work through a couple of steps here. Multiplying both sides by the square root of n. Dividing both sides by 25. Squaring everything, so on the left-hand side, just take the radical away. Then 1.96, 425, take all of that and square it. Well, I lost that. I'll just rewrite it here. I'll rewrite what I had there at the end. 1.96 times 400 divided by 25. All of that squared, and I get 983.4. Always round up, so 984 or more. Okay, so in problem 2, we're trying to estimate the population proportion. We have no prior estimate, so that means that we're going to use 0.5 for both P and Q. We want to be within 0.04, that's the margin of error, and 90% confidence. So margin of error is equal to 0.04. 90% goes with Z equals to 1.645. So P hat plus or minus Z, just trying to put this in the context of what we already know. And so we're going to set margin of error equal to Z square root of P hat Q hat over N. So we have 0.04 is equal to 1.645 times the square root of 0.5. 0.5 divided by N. So the first thing I would do on this one is square everything. 0.04 squared is equal to 1.645 squared times, just take the radical away, 0.5 times 0.5. If you want to multiply that out and put 0.25, that's fine, divided by N. Multiply both sides by N. I am going to go ahead and multiply the 0.5 and the 0.5 there. Divide each side by 0.04 squared. You don't have to do this next step, you could just solve that. But if you want to save a couple of keys in when you're putting in your calculator, 1.645 divided by 0.04 squared times 0.25, and that's equal to 355 about 2. So you need greater than or equal to 356. Again, always round that up. In part B, we know that this is 70%. So if we were doing that, the changes would be here. We would have 0.7 and 0.3. Same thing there, 0.7 and 0.3. Here, if I multiply those, I would have 0.21, 0.21, 0.21, and awesome. It would appear that when I calculated this out, I did part B first. So, come back on my math there. I'll just eliminate this part. Okay, number two. Number two, we're trying to estimate the population proportion. And in part A, remember, if we're going to estimate the population proportion, we already know it's going to be p hat plus or minus z times the square root of p hat q hat over n. So we already know that. That's what we want to. That's what we use. The formula we use to estimate the population proportion. So now what we want to know is how large a sample should we take if we want to be within 0.04. That's margin of error. With 90% confidence. So z is going to equal 1.645. And we have no prior estimate of p hat, so we're going to set that to 0.5. So no prior estimate. So margin of error is equal to this right-hand side up here, z times the square root of p hat q hat over n. So we have 0.04 is equal to 1.645 times 0.5 over n. Now we want to solve this, just an algebra problem now. I'm going to square everything. 0.04 squared is equal to 1.645 squared, and then 0.5 divided by n. Don't re-square the 0.25 there, or 0.5 times 0.5. We've already done it. So now I'm going to 0.04 squared multiply n by each side. If you wanted to go ahead and make that 0.25 there, you could. N is equal to 1.645 squared divided by 0.04 squared times 0.25. You can go ahead and solve from there. What I usually do is go ahead and group those items I'm going to square into one and then 0.25. And that's equal to 422.8. So I want to take a sample of at least 423. So in part B, now I have a pilot study that says we have 0.7 or 70%. We still want the same margin of error and the same level of confidence. Of course, the easiest thing to do at this point is the only thing that's going to change is the P and the Q, and that was 0.5 times 0.5, but now you would have 0.7 times 0.3, which is 0.21. So if you already have this in your calculator, just hit second, enter, and change this to 0.21, and you'll get the answer. But working it out further, we would have 0.04 is equal to 1.645 times the square root of 0.7. 0.3 over n. And I'm just going to do a bunch of steps at once. If you can go from here to the next step, fine. If not, go through the same steps as above. So I'm going to have n is equal to 1.645 divided by 0.04 squared times 0.21, and that is equal to 355.5 0.16, so you need at least 356. One other issue, it's not in this problem, but let's consider a little bit about the value of this information. Because we know that it's 0.7, we're multiplying by 0.21 instead of 0.25, and we end up having a smaller sample size. So that's equal to 67. So we can take a sample size that's 67, in this case 67 fewer employees. Let's say that whenever you do this, that it takes some time to look that information up, and let's say that it costs $10 to look up this information for each person. Probably may not be that much, but let's say it is. That means by knowing that this was 0.7, you would have saved $10 for each person here, and so you save $670. Now, the further away from 0.5 that you get, the more money you're going to save. So let's say that we had an estimate that was 0.1, we'll say. So now, when we get over and do our formula, we're going to have n is going to equal 1.645 divided by 0.04 squared times 0.09. And that's going to equal 152.2. So you would take 153. Again, I'm just making this one up as I go here, which means that the value of that information, the value of knowing that this is 0.1, would be 423, the sample size you would that you would need if you had no prior information, minus the 153. So now you've taken 275. In fact, if you look at it, you've almost cut this, well, you've cut it by over half, almost 2/3. So instead of taking a sample of size 423, you only need one of 153 if you are pretty sure it's going to be around 0.1. And there are many cases when you know that.